are Amy Bordy and Andre Coleman from the Pacific Northwest National Laboratory, and Joe Aga and George Pierce with Rika UAS. Those guys are the company that we use to that we've hired out to work on our drones and a lot of the different instrument integrations. So today I'm going to be talking about our use of drones in the remote sensing of intertidal habitats. And I'll first go through our basic methods, instruments that we use, and some of the analysis, and then focus on applications of the work. So we've been doing this for a few years now, starting off in the Columbia region, looking at restoration and natural wetlands, trying to use our instruments to remote sense vegetation patterns there. We also looked at some dredge spoil islands, and then we moved into Willapa Bay in 2020 to do a baseline study on the tidelands. And okay, so for our program, we actually use a few different instruments that we fuse into a data set, depending on the imagery that we want to get and the different habitats that need to be examined. And so these include high resolution RGB, which is like your regular digital camera, but we use some really high resolution stuff. Are you still seeing me?
Yep, you're good.
About that. I see something different on the screen. Okay. Our second main instrument is a hyperspectral imager. This looks at very narrow wavelengths of light, but over a broad spectrum. And we use this to construct spectral signatures of different objects that we can then use for remote sensing identification. Our third major instrument is LiDAR, which uses LiDAR pulses to look at micro topography. So we're getting like 3 millimeter accuracy on things like tidal flats, which is fantastic. And then a final one is, which we haven't used too much yet, is a infrared camera, which could be used for things like roosting birds or pinnipeds roosting on islands, things like that. We haven't integrated that yet. But these other instruments we kind of put together into a package depending on what we're trying to discern from the environment. And we use a hexacopter for most of these things, which can carry a big payload. And these drones have been automated to a high degree now, so we can actually pre-program the flights in different areas, knowing about overlap and things like that, which are crucial for a solid picture. And then the drone will pretty much fly itself on the predetermined path. So a lot of this is becoming heavily automated, which is really great. Okay, so one key point that's that we need to do is calibrate all these different instruments, and we do that with ground control points. These are all spatially rectified in the environment. So basically, the crew goes out with GPS of different sorts and some kind of quadrat, and where we look at the different plant species, eelgrass, burrowing shrimp, whatever's out there is categorized and spatially stamped in the field. We also use we recorded spectral signature using spectrometers, so we know the radiation that's coming back out, and all these things are then put into a modeling technique in order to train computer programs for each of these instruments. Here's kind of a workflow. Once we have our calibrations from the field, we can then program our flights, go out and fly a large area very rapidly and create a, basically a giant data set. And depending on what we want, we can have hyperspectral imagery, LiDAR, RGB. All of that then is brought into the analytics section. And again, we have these calibrations that we've made. Then there's a machine learning capabilities where we're training algorithms to identify these spatial and light data and identify them in the field. And after that's done, we can query this new data set and produce things like categorized maps and statistics. So here you see a raw imagery of a hyperspectral and it doesn't look like much, but because each of these things are identified, we now know what all these different areas are. And the beauty of that, of course, is that you can derive statistics and things from all this information. So now each of these is identified for a species, and you can compute its area, its density, things like that. So we can extract a lot of information from hyperspectral stuff, and we're getting better and better at automating all this. So there are lots of applications for this, of course, but I'll highlight some of the main ones that I think are important for some of the intertidal stuff. And one is just simply that you can measure large spatial areas accurately now. Whereas before, you'd have to go out and take a lot of measurements. Now it's just like a very rapid process. But the main thing that I think is most useful for it is because the drones are really adept, you can go out and fly them quickly and get all this information. You can do habitat change analysis. That is, you go and fly exactly the same flight patterns a couple of times, and then you can actually measure very precisely how things are changing over time. So this is really important for things like looking for invasive species or monitoring your restoration site to make sure things are actually going the way you want. Geomorphic evolution, you can see things like landforms change. And the real importance, though, is that by doing this, there's the ability for management to be enacted if you see something's going on. Like if the invasive species are increasing, you can go and do something about it. And the other thing that we haven't really done yet, but I think is super exciting, is to use this technique, the change analysis, for experiments. So you can go out, say, in Willapa Bay and do some kind of a treatment effect on burrowing shrimp, say, for instance. And then instead of going out and having to monitor the shrimp with, with shovels, you do it by the air. So this way you can actually do broad experimental programs and get a change analysis and using a response variable as, something that is now remotely sensed instead of going out in the mud. So we haven't done that yet, but I think that is a super exciting aspect. Okay, so let's talk about a few applications. First, we'll talk about some change analysis from wetlands, then a dredge spoil island, how we can look at changes there, and then finally, what we found out from our baseline study in Willapa Bay tidelands. So again, the restoration trajectory, using the same flight patterns over different times. This is just a couple of months, but you can imagine this would happen over years to monitor a wetland restoration site. This is the RBG imaging, so you can see how high intensity that is. But this is the hyperspectral pullout of that information. And here are some of the data that you can extract from it. And in this case, I'm highlighting an invasive species, reed canary grass, which in this case actually decreased over the 4 months or so. But in other cases, this might be a warning, like you want to monitor this, just make sure that it does not increase much. And if you see that it does, actions can be taken to go out and remove it. This has applications for, say, Spartina in Willapa Bay, the same general idea. Here's another example. This one is from some LiDAR data that we took in Miller Sands. This is the Corps of Engineers is trying to do more in-river dumping of sediments. And basically, we need a technique to actually monitor where that sediment goes and how it affects the habitat for other creatures. So here you see the LiDAR, and these are actually the mounds of sand that were dumped by the pump system that they used to put it up here. And we went back to 2010, found some older LiDAR, and then compared it to our data that we take, and you can subtract those to see what's remaining. And in this case, it's something like 42,000 cubic meters around here. But not only that, you can see the spatial distribution of that. So here, this high point is where the sand has accumulated, and some of these blue places where it's actually been eroded and it's lower than it was. So this kind of system, again, you can monitor where things are going and affect change if you see there's problems. Okay, let's move into Willapa Bay. So this was a ground truth study. We only had basically a couple days to make all these measurements during the pandemic. It was kind of crazy, but we managed to do it. And this whole idea was to try to remotely sense burrowing shrimp, eelgrass, oysters, and benthic algae, things that were out there essentially. Here's an RBG of Nakata showing our ground truth paths. All these little red lines are where people went out to make different measurements of the habitat. Here's just a blow up showing some of the detail. This is somebody's track. And then here you can see the eelgrass and oysters that are in a blow up here. So this is the oysters and eelgrass, and here's the categorized data. And the white is all the oysters. All these, the green is basically Zostera marina, the native species. But we also have an ability to sense the introduced one as well. That's just a blow up. But here's the actual data from the whole site that we surveyed in Nakata. Again, all these little white things are where we took ground truth measurements. And then here you see the ability to scan this whole area and extract out areas and percents, and also measures of precision, how well we think that the modeling actually was able to discern things. So pretty good, actually, identification. Overall accuracy was about 83%. So there's always room for improvement in these models and things, but as a first cut and as our baseline thing, we were actually pretty happy with these results. We also went out to Oysterville and did a kind of a different pattern, a long strip going from offshore to onshore. This was mostly eelgrass, and here you can see the different eelgrasses are pretty well discerned in this pattern. Here's a blow up from here. And again, you can extract information like this to determine the present day distribution. And remember, we could do this again over the same exact flights and see how things have changed over time. Then finally, the burrowing shrimp. We had to use kind of a different technique here because obviously we can't see the shrimp. So we are looking at their burrow mounds as an index for their activity. We had to use LiDAR and the RGB kind of together in a model to estimate this. Here you can see a blow up from this small area where we're looking at the mounds here. And as the process goes on, then we can make a model showing where the densities are. It's a heat map. So these are the high densities of burrowing shrimp on the site versus low densities. 92% accuracy for the shrimp, we think. So those are some examples of the remote sensing techniques as we are doing it. We think for restoration sites, these vegetation complexes, we were able to identify something like 25 to 30 individual plant species and their associations with high accuracy. We think the intertidal stuff has come along well, but it was only baseline study, so more work should be done there to hone things up. But the techniques seem pretty solid that we can use these methods to actually make high density spatial measurements. We can move into other things like harmful algal blooms, and as I said, with the LiDAR, the FLIR camera, look for bird colonies, things like that. So right now the process works pretty well for high resolution data. Repeat sampling is the method to use to see ecological change, and that can be used for experiments or just monitoring different things. We are close to operational status, but there's more tweaking that definitely could be done. And all the time, this technology really is changing quick with different instruments and new analytical techniques, especially. So it's kind of exciting to have all this information, and the future for this is obviously going to be pretty bright. Okay, with that, I'd just like to thank for the funding, especially Washington Department of Agriculture, who funded the Willapa project, and thanks to Mike Norton and Dave Bigley for their help in the field and getting the projects done, and of course Pacific Conservation District and Taylor Resources let us make the measurements out in Oysterville. And we have a couple of reports out for more details if you are interested. So stop there and take some questions.
Thank you very much, Curtis. Our first question is from Chris on chat asking, does vegetation need to be completely exposed to differentiate species? Could ZOMR and ZOJA be identified underwater? And if so, how deep? Suppose it depends on water clarity.
So we try to pick really low tides so that everything is intertidal, exposed to air. You can do some things in shallower water, but it takes more tweaking, so it's not as clear. A lot of light, of course, is absorbed, so the reflectance pattern, it would be different. But you know, it probably could be worked out if you had shallow subtidal areas that with eelgrass. That's what the Zostera are. Those are both species of Zostera, by the way. But I think it could be done. We haven't done that, but it's just a matter of making the calibrations. You know, the light on the surface is a tricky thing because it can really reflect the light. So you want to standardize how much you're taking these baseline studies and for the calibrations. So basically, we try to make all the conditions as common as possible, so that you don't have to do a lot of calibrations. And I should note that, you know, as we went out there and did all these things in the field, hopefully you don't have to do that all the time. The real strength of this is once you have your calibration curves and spectral signatures and things like that, you only have to do that once for the different species. If you go at the right time of year and things, then you can go to new places that you've never sampled on the field and still be able to extract information. That's a big strength. So we don't want to have to go out in the field all the time and make the calibrations.